Okay, when you're drawing the positive and negative terminals, it's technically it doesn't really matter like which goes in the top and the bottom, whichever you prefer. I personally prefer putting the positive on the top, sometimes in the bottom, but in this case, let's put it on the top. It suits for this question because we have positive charge sphere is given. So two plate X and Y, assume this is X, and plate Y is set up in the 10 centimeters apart. So the separation is 10 centimeters again. It's connected to the positive terminal of the 60 volts. So what we have is a DC battery. Goes like this, and 60 volts is kind of applied in here. All right, and a small positively charged sphere is suspended midway between the plates. So midway as in like is in the middle here. That's a positively charged sphere. And it experienced the force of the force given is 4.0 times 10 to the power minus 3 Newton. Now, one question. Does it really matter for the position of the sphere to get the force? Okay, what I'm asking is, if we have spheres on the top, at the bottom, does it affect, do the positions affect the amount of force gained by the sphere? It does not. You have to answer that because they're in the electric field, just like I think of the gravitational field. When you're jumping, you're standing on here and there, your weight, the force due to the gravity will be the same. Okay, it means that they will carrying the same amount of force. Do not confuse that point. Again, understand what I mean by the force too. Then, what would be the size of the force on the sphere if it was placed 7.5 centimeters from the plate X? As I said, doesn't matter, same force, regardless of the position. The force is uniform. Therefore, the force experienced by the sphere would be same, 4.0 times 10 to the power minus 3 Newton. Again, try to understand what I mean by the force. Force is about like making something to move. Yes, it will affect the giving some extra acceleration, which will have a different type of different amount of the velocities later on too, but it's not related for question A. B. The sphere is placed back into the middle and the plates are moved apart to a separation of 15 centimeters now. How does it affect the force now? What we have to consider is F depends on the QE. Okay, so before I just jump into the calculation, I want you to understand that force is directly proportional to the E. Okay, which means greater the E, the greater the force they applied. Smaller the E, smaller the force applied in here. How do you find the E? Q. E is the same as the Q, the voltage divided by the separation of the plates. Now, the question is giving you that. We're given that 10 centimeter separation, now move to 15 centimeters. So the new E, it would be the V on the D. That is same voltage, 60 divided by, in this case, instead of 10 centimeters, we have 15 centimeters, which is 0.15. There's a new E value. Therefore, 60 divided by 0.15, you're to get 400 newtons per coulomb. Yes? Yes. No, D here. I'm talking about electric field strength. It's always the D. Always the separation between two plates. Is that things related to the separation for the electric field strength? Remember that what I mean, the D and the E, the relation between here. That's not the position of the particle. It's always the separation between two plates to find the electric field strength. Okay, it's not about where the sphere is. So, what is the sign of force? That's given. So, therefore, the force is now be given the charge. You're not given the charge from A. Actually, we need to find it from A. The F was QE, or simply Q, is found in F on E. That is 4.0 times 10 to the power minus 3. Previously, it was the electric field strength of the 60 divided by 0.1. That gives you the charge of the sphere. Are we given the charge of sphere? I don't think we're given. So this is something we need to find previously. Then 4 times 60 divided by 0.1 and 4.0 times 10 to the power minus 3 divided by that, you're going to get 6.67 times 10 to the power minus 7 coulomb. Therefore, the new force on the question B is Q times E. That is 6.67 times 10 to the power minus 7. That times E value 400. Times 400, you're going to get 2.67 times 10 to the power minus 3 Newton. It's a new force that is applied. So compared to the initial force, it's actually, we can see the decrease of the force from 4 to 2.67. So, sorry, I need to match up the sig figs. It'll be 2.7 times 10 to the power minus 3 Newton in 2 sig figs. Make sure you match up the sig figs too. C. The plates are returned to a separation of 10 centimeters, but the battery is changed. The force is now 6 times 10 to the power minus. So typos, there should be 10 to the power minus 3 on the top. Newtons, what is the voltage of the new battery? So the D is now came back to 10 centimeters, but what we have now is force. It's given as 6.0 times 10 to the power minus 3 Newton. That's given. If you realize that, this is founded by Q times E, where we share the same Q value from question A. We can think about the E would be 6.0 times 10 to the power minus 3 divided by the E value, the Q value. That's the same as V on D here is this too. So the voltage is therefore 6.0 times 10 to the power minus 3. That times the D value, which is given as 10 centimeter again, so 0.1. That divided by Q that we found in here, 6.67 times 10 to the power minus 7. And that's it to find the voltage. I just rearranged this formula here. This is from F equals QE. That's the definition of the E. Make sense? Then you get 6 times 10 to the power minus 3. That times 0.1 and divided by 6.67 and 10 to the power minus 7. You get 9.0 or simply 900. No, the voltage is the final answer. Is that right? Did I do something?
Because I used the exact value of Q.
Which is that value. Is 10 to the power minus 7 the right value? I just confirmed that.
It's 1/137. So I used that value.
Which is that? Oh, sorry. Oh, gee, yeah. That's 10 to the power minus 6. Yeah, calculation. Which makes sense. This is 6. That means need to change that. Sorry, guys. Okay, that times 400. For the previous answer, then it'll be 2.7 times 10 to the power minus 3. Oh, I got it right. This one. Yeah, it should be 90 then, because we decreased the value. So it should be 90, then 900. Okay. Oh, give me a second. All right. Oh, that's history. Let's move on to the second part of today's class, which is about another field. No, we did that. Okay. So page 11, please. Something that we discussed previously about the relationship between the charged particle or the current to the induced B field. Okay, one thing that you must understand, you don't have to understand, one thing you need to memorize or remember is when there is I, it produces some induced B field. Okay? It simply means when we have electricity, any of the electricity, like in this kind of all the electricity here, it will produce a certain amount of the magnetic field. We will come back to this when we talk about motor effect, probably next week. Now, why is this so important? This kind of gives you the idea here. We believe that there is no relationship between charge and the magnetic field before. Okay? And scientists actually investigated through that. They found that there is a close relationship between charge and the magnetic field. This is simply just, I describe that as when there is R, it produces the B. This is how I describe it. Okay? Does it make sense? So something you probably learned a right-hand grip rule that's saying when there is a current carrying wire, it produces the magnetic field in this direction. Okay, we'll come back to this next week because this is something that's very important, and this is the essence of the essential for you to understand motor. Now, why is it so important? Now, when we then put some particles in the magnetic field, because we know that there's a relationship between charge and the magnetic field, scientists investigated through that here. What if we put charged particles actually I wrote it right at the top. There's something that's more important. Charged particles in B field. Again, try not to understand, just simply remember. I will probably ask you to memorize this a bit here. Scientists found that from their investigation that when they shoot the possibly charged particles into this, moving into the velocities. Now, I'm showing you the B field in the green. In this is the B field. Again, B stands for the magnetic field. When the charged particle goes into the B field, as like they're producing some sorts of the magnetic field, there will be interaction between two magnetic fields. I describe that as this. Remember that the direction of the positively charged particle, this is same as direction of the current. Okay, so which means when we have a positively charged particle moves into that, I just take that as this is same as the direction of the current. Does it make sense? Okay, again, just accept it. This is a matter of the accepting or not. Means we have a positive charged particle moving into a certain direction, same as the direction of the current. Okay, it means that we can now apply the right-hand grip rule. That using my right hand, the thumb indicates the direction of the current, that it shows the magnetic field or induced magnetic field that's coming into like this. As you can see, on the top of this arrow, it comes out of the page, coming out, coming in like this. Can you imagine this? You actually need to use your right hand quite a lot for this module too. Means I can redraw that this part over here would be coming out of the page. Does it make sense? Okay, this part over here is coming into the page. Now, remember that this the purple is the induced B field. this is somewhat different to this original B field that we have. Okay, induced B field means that this is the magnetic field produced from the current or the movement of the positive charge. Make sense up to this point? Then the simple rules applied. As we discussed the prime rule of the charges that opposites attract. Same rules applied in the magnetism. That you probably know that, like north and south, they attract. North and north, they repel. Why is that? Because they're in the same direction. Same charge, same polarity will repel, opposite attract. Same rules applied in here. Then can I use the same rules in here? What I mean is we have this part and that part, the same polarities. Okay, or same direction. Okay, Steph, what do you expect between these two then? If we have just assume that we have two magnets, same direction, same north pole, what do you expect? They repel. So this is how we interpret in physics now. We have a same direction, the magnetic field means they will repel. What about this part over here? This is coming into the page, coming out of the page, opposite attract. So this is the part where we get attraction. Does it make sense? So let's see what happens then as it goes in here. So I redraw that magnetic field. I show you this. We have something goes I, or the positively charged, the particles goes in to produce that magnetic field coming out of the page into the page. Remember that purple is induced. Purple is kind of produced from the I. Then as these two, the magnetic from the green and purple are attracted to each other, this will move towards to that. At the same time, it will produce this. It will move towards to this direction. That force is generated. Yeah. So what that happen is the proton, this proton or the positive charge will be moved towards to up or towards this direction, perpendicular to the movement. Now, it's going to make this kind of movement the two. What happened in here? It will be still the same. I showed in large picture. We have a particles. The force is applied. Now it's moved to this direction due to that force. Think about what happened. We still have the magnetic field due to that induced current. So the current. So it will move towards there. Okay. If I extend the magnetic field, it will make this motion. That always having the force towards the center. What is this? Circular motion with the centripetal force applied. What produces centripetal force in this case? It's due to that interaction between two magnetic fields. One from the permanent magnet in green, another from the purple from the current. Okay, so the charged particle which is moving into the magnetic field it now have the circular motion due to this reason. Okay, it's hard to understand, so this is why you need to accept it that this is what actually happening. Does it make sense to all? Okay, now then how do we figure out the direction? This is where we use something known as the right hand palm rule, right hand push rules. There are many names of that. I prefer, this is something in all syllabus way, FBI gun. This is why we don't really use in the syllabus. We don't, because the gun naming, the weird shape of that fingers, we don't really use that again. This is also known as the Fleming's right hand rules. Rather than using, some school teachers actually use the right hand slap rules, palm rules, push rules, doesn't really matter. They're talking about the same things. I hope you remember this. Just use this right hand rule, right hand palm whatsoever. That started from here, this is actually easy, making this a kind of gun shape. The middle finger stands for F, index B, thumb I. FBI. Easy as that. Okay, where F stands for the force applied to the charged particle. B stands for the B field produced inside the permanent magnet and permanent magnetic field. I stands for the direction of the current. Okay, and this is the reason why I emphasize that the direction of the positively charged particle is the same as the direction of the current, which is the thumb value here. Then what I do, I'm applying these fingers to see that determine the direction of the force applied. How do I do it? Use your index fingers to point it in. The X stands for the going into the page, yeah? So your FB magnetic field is going into the page like this. All right, then what do you have for the I? The direction of the I is going like this right here. I know it looks weird. This is why we don't really use it in schools a lot, but you can use it. This is why we use a palm instead, taking the palm as the force. I prefer that. You never forget that. FBI, you never forget the FBI gun. You can't forget about the palm rules, but this is something they're very easy. I know it looks weird, especially in the videos sometimes too, but we're learning. Okay, sometimes this helps. So that middle finger is indicating the direction of the force. So as you can see, this will apply the force every single time. You see that? I'm moving that direction of my thumb, which is indicate direction of the current of the positive charge. It makes it goes into the here, just like this. Goes in like this. So making a what? Uniform circular motion. Confused?
Can you explain the hand rule again?
Hmm?
Can you explain the hand rule again?
How, sorry?
This one, things variable.
FBI or right hand palm rule, same thing. You may use anything like you would like to, but my personal way, like FBI, whatever, FBI, you never forget, okay? F stands for the force applied on the charged particle in the B field. Okay, write it down over here to explain. From the FBI, F stands for the force applied on a charged particle. B stands for the permanent magnetic field. Remember that the permanent magnetic field is kind of existed before that the movement of the eye. Okay, I'm not talking about induced B field here. I'm just using this induced B field to give you some understanding of why you're making the circular motions. So even if you don't really understand why now, it's okay. We're taking more time to understand the point in here. But what I want you to accept is the B is simply the permanent magnetic field you have given. Then I is out of B, direction of the current, which is the same as direction of the positively charged the particle. And if the direction of the current is the same as the direction of the positively charged particle, which means this is the opposite of the negatively charged particle. So opposite direction, I should say. Okay, so I'm going to stick on to the positively charged particle for now because I don't want to confuse yet. Just simply apply the right hand. Okay, don't use the FBI guns in your school syllabus because it's out of syllabus now. I prefer that because even though it's old, it's much better. I assume that the reason why they get rid of the FBI gun or the flaming rule is because of the name gun. They don't want to use any terms that we still do use that. Okay, that's how we can determine. So how do we do it? I'll give you some other situation here. The rule is very simple, and the way you apply your right-hand palm rule is quite straightforward. So give you the situation here too. Assume that we have magnetic field. That's a B field. Okay, and we have the positively charged, like the proton. Let's say helium alpha particles. I think I prefer that. Alpha particle goes into the field. Determine the direction, therefore the movement of the alpha particle inside the field. Again, try not to understand. Just simply use that. As simple as this. Okay, F, B, and I. If you remember that index finger is a B, that's coming out of the page like this. Okay, coming out of the page. Step, you okay? Index finger stands for like the direction. Fingertips indicating direction of the magnetic field. What is that direction coming out of the page? This. Yeah. Now, it looks weird. Okay, to do this. Direction of the alpha particle. Remember that we discussed the alpha particle is helium nucleus, which is positively charged particle. If you remember that alpha particle is then having the same direction, the current direction would be this, the thumb indicating to from my left, from right to left, going into this direction. Okay, the finger, index out, thumb to the right. Then what is this? Looks weird. Okay, the palm facing upwards so that force is applied into this direction. That's all you need to do. All you need to do. You don't need to understand any single bit. Just need to use your right hand, because everyone, not everyone, but I assume that everyone can use the right hand to find out the direction of the force. Okay, which means what? This alpha particle inside of this B field making the circular motion, because every single time going into this direction, it applies the force towards that. So making the circular motions like this. Does it make sense? Okay. Does it make sense? Okay, this is set. Think straight. Don't overthink about it here. Just use your right hand to find the force direction. That's all you need to do. Okay, which means it's making the upwards, making this. What is the direction of this circular motions? This is called the clockwise direction then. Which means alpha particle inside of this B field will make us clockwise, make a clockwise movement. That's it. That's it. If you want to get deep into it, apply the right-hand grip rule to understand why the magnetic field is kind of repelling and attracting to each other. That is the explanations. But as I said, try not to understand the point yet, because it's too much for now. We will come back to this next week when we talk about the multi-effect. But something that's very important, right-hand palm rule, right-hand FBI gun or right-hand palm rule, whatever you want to use your right hand to find out the direction of the force. Then, Oren, what would be the magnitude of the force applied in here? What would be the magnitude of the force applied to the alpha particle? In other words, by me, F. There are two methods, but I just want you to know one for now. We have a circular motion. We have a circular motion. Yeah. In any circumstance, you have a circular motion. I told you like that net force applied would be always with circular motion, mv squared, the centripetal force. Same as centripetal force. That's one force that we're going to use. What is the m, mass of the alpha particle? What is the v, the velocity that's moving into the field? What's the r? That's the radius of this circular motion. Yeah? Now, this is something that relates to mechanic side. Now, related to these into the electric field or like some electromagnetism, F in this field is also known to be this. It's easy to memorize. Queen Victoria Building, sine theta. That's it. The V stands for not the voltage, the velocity, by the way. Queen Victoria Building. QVV sine theta. You will never forget that. FBI QVB. Okay, simple terms. So the Q stands for the charge of the particle moved enters into the field. V, which is the velocity is moving. B stands for the strength of the magnetic field that you have. Sine theta is the angle. So which means is if that comes into, so I want you to think about like a direction of this magnetic field. It's coming out of the page like this. Can you imagine this? Okay. Now, the particles move towards to that, into the left to right. So if you see the angles making the perpendicular like this, Yeah. Now, what if we have particles going into the page or out of the page? What about the angle made by the movement of the particles to the B field? It'll be 0. Does it make sense? So particles moving to this direction is moving to this direction. There'll be 0. It means that there will be no interaction. This is why we use sine theta. Where the theta stands for the angle made by the movement of the particles to the direction of the B field. Does it make sense? Which one? When it's 90, means that it will have the maximum forces applied. So like this. It's coming out of the page. Can you see that? The rule is coming out of the page. Okay? Particles going in like this. From your right to left. That means you're making the perpendicular angles like this. Now, if the particle enters like into this direction, we will not have any interaction between them. Accept it. Try not to understand. Accept it. Okay. This is also related to the induced B field, but this is too complicated. Just try to accept that as, oh, okay, when the particle enters to the B field perpendicularly, it has the maximum force. Okay. When it's making the parallel, there's no force, which means in between, the force will be decreased. Does it make sense too? Okay. It's very important because you got to get a lot of sine and cosine in module 6. Very important to imagine, use your hand, use your brain, use your feet, whatever, your body parts to understand the angles approaching. But that's what I mean in here. Looks complicated, I know that, but if you get some question related to this, it's actually pretty straightforward. That question is simply asking you something like this. We have question page 13, please. A single positively charged particle with a charge of 1.6 times 10 to the power minus 19 travels at the velocity of 10 meters per second at an angle of 30 degrees to the magnetic field. Strength of 4 times 10 to the minus 5 Tesla. What is the magnitude of force that particle will experience from the magnetic field? So how do we do it? It's simply F equals to QVV sine theta. This is it. This is, yeah, okay, QVV sine theta is in your formula sheet, but I recommend you to memorize it, just like you're memorizing the half mv squared of the key. Substituting all the values in, we have 1.6 times 10 to the power minus 19. That times the velocity is moving in 10 meters per second. B field strength of 4 times 10 to the power minus 5. Now, sine theta, that's sine 30. Okay, so instead of going into perpendicular like this, it's making the sine 30 angle like that. Doesn't really matter for the direction here. And use your calculator. That's it. 10 to the power of the minus 19 times 10 times 4 times 10 to the power minus 5. That times sine 30. You'd get 3.2 times 10 to the power minus 23 units Newton. We are not able to determine the direction because we're not really given the direction of the magnetic field nor the direction of the charged particle moving. So we just leave the magnitude here like this. What about next one? A single negatively charged particle with the charge of the minus 1.6 times 10 to the power minus 19 coulomb is traveling horizontally out of the computer screen and the perpendicular to the magnetic field that runs horizontally left to right across the screen. In what direction would the force experienced by the change act? Can you give me about 30 seconds? Can you draw a diagram? You need to have a little bit of skills, drawing skills, but not as much as in visual art. I better do this. Okay. So assume that we have a computer screen. It's ejecting. So a computer screen is like ejecting the electrons out. So assume it's coming out like the electrons coming out like this. Okay. It's giving you that magnetic field that runs horizontally from left to right. So we have a magnetic field, B field, goes like this. And it's specifically giving you that they are perpendicular to each other. Yep, let's give it. And perpendicular to the magnetic field. Does it make sense? Okay. Then what would be the direction? You do not need to calculate anything here. You actually need to use your right-hand palm rule. That's it. That's all you need to do. But one thing that you need to understand here is we do not have the positively charged particle. Instead, we have a negatively charged particle, which means, I hope you remember this, direction of the I is opposite to the direction of the E minus. Yes? No, it's not down. It's coming out of the page. I want you to think. Imagine, because I can't show you that. It means this. Down would be this, but it's not really like. I want you to think about in 3D, in the 2D, in the whiteboard. It's hard. It simply means electrons coming out of the page like this. That's the only way I can show you that in the 2D whiteboard. Okay, the way you can show that is visual art. That's perpendicular to the surface. Yep. Okay, or you can do it like this. We have a screen that's lying down, electrons coming out, B field coming to this. Doesn't matter. It'll be the same. Okay. Now, what we do, you still apply the right-hand palm rule, that FB icon, to determine the direction. So what we do, take the B first, use your index finger to determine the direction of magnetic field. That's from left to right, go this direction there. Okay? Index finger, the B field. I is the problem there. This is the direction of the current, which is same as the positively charged particle. But as I said, it is like opposite. This is something that you have to think. Okay? So your direction of the electron will be determined by the thumb, which will be opposite to the eye. So if the electrons comes out of the page like that, the direction of the eye would be actually going in like this. So give your middle finger or the palm facing down. Again, don't try to understand. It's a simple rule, it's a simple logic that direction of the electron is opposite to the eye. Or I has the opposite direction. Now, I know this is kind of confusing because we have a positive and negative. Okay? Proton would be the opposite direction. We take the same direction of the proton. We take the equal direction. So it means that if the proton comes out, that'll be the direction of the current. Goes up like this. Yeah. You okay, Steph? You look confused? Why is not that one? Because we have an electron. Again, try to not to question or understand here. Just try to accept that, oh, okay, the direction of the current, I, is opposite to the direction of the E minus, or the electron. So B going there. Can you say to my hand, fingers, index finger, okay? Now, thumb, because electrons coming out of the page, means that we take the opposite direction of the electron that's going into the page. So this is why my thumb is facing in. Then middle finger, all the palm is facing down. The force will be then going downwards. This is the direction of the force. I'm saying this again. Don't try to understand the point. Just try to accept it. I'm just giving you a shortcut to solve some questions like this. Okay, now, another way to figure out is, I'll give you this. We have a fear of this. Is it out of syllabus method? We have a right-hand palm rule. I call the F right hand FBI gun. Same thing, okay? Taking that, give it this. The direction, your thumb, your right hand, okay? Your thumb it has a direction of the FBI, same as direction of the current and positively charged. Particle given here. Okay? Everyone good to here? Okay? I teach you, I just give you one more rule that is not part of the syllabus, not part of the workbook too. There is actually the left hand FBI gun as well too. So we call that Fleming's right hand rules, Fleming's left hand rules. Okay, now what I do here is the thumb of your left hand would be direction of the negatively charged particle. So instead, okay, this is the thing. Instead of you thinking about the direction of the current from the direction of the E, simply use your left hand. If you have something negative, use your left. If you have a positive and current, use your right. Okay, then how do we do it? Same rules, F, B, and I. F, B, and I is in like in the electrons too. Then you see that B is going into this direction. I is coming this direction. You see the force is facing down straight away. Okay, this is a rule that I can teach you. I would probably use right hand left rule again. Out of syllabus, you can't really say that you use a left hand palm rule, but in the exam, to save your time, to save your brain energy, use your left hand. Okay, if you use a left hand, it takes about what, 1 second straight away. But if you use a right hand all the way, there are too many right hand rules. So it will make you confused. You get the right hand grip rule 1, yeah? You get another right hand grip rule later on. So I try to teach you some different rules, the hand rules that you can figure out the direction. Does it make sense, Steph? Okay. Remember that in the left hand palm rule or the left hand FBI gun, your thumb is simply the direction of the negative charge or electrons. Okay. This right hand, that's positively charged, alpha particles, protons, positron, whatsoever. So I give you one question that we had in HSC before. I hope I put that question here, which I didn't. Okay. Okay, page 14 actually gives you good ideas here. So we have an alpha and beta comes out from some radioactive part, the transmitting what I call like some matter. Remember that alpha particle is a helium nuclide, which is positively charged. Beta particle is simply an electron. Okay, now use your right hand palm rule. You can determine if it comes out alpha particle is a positive. This is positively charged. This is negatively charged. Positive right hand palm rule straight away. Okay, F, B, and if you're confused, use the FBI. FBI. That's easy. Then use your thumb, use your index finger to determine direction. This is X means going into the page. Going into the page. Okay. Thumb indicates direction of the positively charged. Going there straight away, you get the thumb, your middle finger, the palm facing up. This is why alpha particle moves upward like this. Okay. It is just what it is. Okay. Now you have a beta particle which is a negatively charged, which is an electron. Use your left hand. Okay. F, B, and I, or the E again. B is going into the page. Okay. This is moving to this direction. You see the middle finger facing down straight away. Okay, without thinking about the direction of the I is opposite to the direction of the E. Yes, you can use that to your right hand palm rule, but this get confused. I try to make a really simple thing. I try to make it really straightforward. Use your right and the left hand palm rules, the FBI guns, to determine the direction of the forces straight away. Simply remember that right for the current and the positive, left for the negative. That's all you need to remember to determine the direction. Does it make sense to all? Yep. Steph, you okay? Okay. All right. The magnitude of net force of charged particle. Okay, let's copy this one here. So what actually happened then? We're going to think about it here that force applied is F equals to QVB sine theta. That's what we given before. I hope you remember that, like in any situations, in any circumstance that you have the circular motions, the net force in any circular motion, the net force is always be the centripetal force. Okay, this is, in this case over here, when we have the interaction between charged particle and the B field, the same as that QBB sine theta. I call that as F due to the B field. Okay. This one? Yeah. No, this is only for like, when the charged particle enters into the B field. But this is equivalent to the centripetal force. Okay, you have to differentiate that. Like, there are there are same magnitudes talking about same thing, like a frictional force and the frictional force to the centripetal force in the car drifting. Okay, but different type over here. So what we have, mv squared over r is given as qvb sine theta here like this. We can derive that later on too. We can cancel out the v and we can make it some magnitude net force. This is the same as the net force value. And we use these formulas quite a lot. Yes, you can cancel out the v, by the way. Okay, but you can get to derive that to get to some r. And this is something that we use a lot in scientific skills again too, to give you some values to figure out what would be the direct proportional relationship between them. Some hint. Okay. Any questions up to here? Again, just accept it. Try not to think too much. This is something that's very simple if you don't think too much about it. Okay. I'm just going to talk about it. Oh, all right. One thing. But what if we have a situation here? So in the E field, let's talk about some difference between E and B field then. In the E field, where we have positively charged and negatively charged plate, when I place the negative electron here, okay, assume that the U was 0. And we just learned that as, that opposite attracts, the positively charged plate will attract that is induce the movement. So there will be a force found by QE. Okay, that's what we learned. But what about in this situation here? What about in B field? That we have a B field like this, or I give the same situation here like this. We have something B is going upwards. Okay, now when I place just the electron inside, I just place that, I just drop that. What happens to this? So U is 0 again too. E electric, B magnetic. E electricity, B magnets. Simple as that. All right, any guess? We know that in E field, it doesn't really matter whether like the electron is moving or not. When we place that, it will move towards the positively charged or opposite charges. What about in here? Initially, electrons is not moving. So in the E field situation, we said there's a net force and acceleration. There is a uniform acceleration. On the stationary particle. Simply, it moves towards the negative, the opposite charged plate. What about here? Can you spot out there's some difference between this to that? This particle here, it wasn't moving. It was initially 0. Okay, think about it in here. I is only produced when the E is moving. Yep. We have a current. We can't get the current in the circuit when the electrons are jumping and running. In a battery, AAA, AA battery, we do not have the current. It's a stored energy. Does it make sense? Okay? Unless it is connected to somewhere. Unless you plug the power. Here, when we have 0, when initially the particle is not moving, means that there will be no force applied. Means that it will be stationary, remains stationary. It only gets, the electron only gets the acceleration, only gets the force once it starts moving, like this situation here. Okay, do not confuse this. This is something we love to put in. We are just simply giving questions like compare or contrast the movement of the charged particle in the E and B field. Mathematically, I can prove that too. Steph, if the particle is not moving in the B field here, okay, what if the V value? 0. What about the force value then? There we go. Mathematically, this is how we prove it. Okay, but don't think that it's mathematical like it is, because this is only be on one small part of your question that you would get. I can ask you like why then it's not producing any force later on. Okay, remember that the force is only generated in the B field when it's moving, in the B field, in the magnetic field. In the E field, doesn't really matter because it was simply attracted to the opposite charge plate. Okay, all right, let's try one question on page 15, please. Let's do that together. This is something combined electric and magnetic fields together, combined question. Yes. In E field, north and south. Do we have the positive and negative in magnetic field? Can we count the positive and negative in north and south? North and south simply be the direction. North means it's coming out like this in terms of the magnetic field strength. Okay, so we don't have the positive and negative in here in terms of charges. That's only for the electricity or electrical charges. Okay, but I know you will. We're learning about think about the module 6 title. This is electromagnetism. You're now learning about the relationship between charges and magnetic field. That we believe that they are separated. They're not really related. Now we started learning about they're talking about the same thing. Okay, again, try not to understand. That's something really, really complicated. It's better to accept, okay, they are interacting, they're related, that's it, okay? Stop your thoughts in there. Just put a full stop. They will stop, that's it. Okay, because there will be time we will coming back to like some understanding, they're challenging you, but not now, because it's too much for you now. All right, shall we do the 1.9 together then? An electron gun releases the electrons, which are then accelerated across the potential difference of the 32 kilovolt over a distance of 30 centimeters between a pair of a charged parallel plate. Assume that the mass of the electron is that, and we are given charge electron. A, calculate the strength of the electric field acting on the electron beams. We kind of did that too. So how do we do this? We do electron field strength can be calculated by E equals to V on D. Simple as that. We have a voltage at 32 kilovolt divided by the distance or the separation between the plate, 30 centimeters or 0.3. That gives you 3.2. Sorry, 32, not 3.2. You're to get 1.07 times 10 to the power of the 5 newtons per coulomb. Okay, that'll be the amount of the electric field strength. B, calculate the speed of the electrons as they exit the electron gun assembly. Okay, could you try the question B? Give you about a minute. We just did that. Don't overthink. For the question B, there are various methods. You can use the motion equations. You can find the acceleration from the force again too. But as I said, don't overthink too much. Just simply use voltage is divided by the kinetic energy divided by the Q. That's it. You will get some of the kinetic energy. So how do we do it? The K is equals to QV, that is half mv squared. So to find the velocity, because we know there is initially the electron was not moving. So delta K is basically same as a K in this case. We ignore the initial kinetic energy, which is 0. Then we get the velocity is equals to 2 times QV divided by m and square root of that. This is kind of generate a formula, or derive the formula too. So 2 times charge of the electron, that's 1.602, times 10 to the power minus 19. That times the voltage there you're given. You're given that it's given as 32 kilovolts, so 10 to the power 3. That divided by the mass of the electron, which is given as what? 9.109 times 10 to the power minus 31, and square root of that. So 2 times 1.602 times 10 to the power minus 19, 32 times 10 to the power 3, divided by 9.109 and 10 to the power minus 31, square root of that. You get 1.06 times 10 to the power of the 10 to the power of 8 meter per second. Yes, you may use a different method, like using the motion equations. You could do that and that. Doesn't really matter. You get the same answer, though. Okay. Everyone good up to this point? This amount of the energy again. C. Then what about C? This electron then travels through the uniform magnetic field perpendicular to their motion. If the field is of strength of 0.2 Tesla, calculate the expected radius of the path of the electron beam. Okay, the expected radius of the path. How do we do it? You're given that. Let's write it down, all the relevant information that we have. The B is given as 0.2 Tesla. Theta is kindly given as 90, so we don't really need to worry about it. Then rest is simply given. So F is given as QVB sine theta, where the Q is given as charge of the electron, 1.602 times 10 to the power minus 19. The velocity is given. We found in question B, 1.06 times 10 to the power 8. B field strength, 0.2 times that sine, 90. That's it. That's all you need to do to find the magnitude of the force. Then you get 3.4 times 10 to the power minus 12 Newton. That's about it. That's all about like finding the magnitude of the forces. Okay. So you may get some other different questions, like asking you to use to find the direction given from the different particles too. I'm gonna bring some more questions about chapter 1 next week. For your homework, could you finish up the try yourself questions from question 2 to question everything actually up to question 11. Okay, they are not easy. Some of them are really hard. Some of them really difficult. But try it. Give it a go.
Wait, so for this question, all we just did,
Hmm.
where does it say radius?
Oh, did it question ask you find radius? Sorry, I misread the question. I must be. Yes. My bad. This is same as MV. We have not done yet. MV squared over R. Actually, I can make that MV squared over R. I can do that. Cancel out the subject to the R. Let's do it from here. R is then equals to mv squared, so mass times v squared over 3.4 times 10 to the power minus 12, which is a force. That is m 9.09 times 10 to the power minus 31. And velocity, there you found it, 1.06 times 10 to the power 8 square divided by 3.4 times 10 to the minus 12. So you should get 0.003 meter. 260 feet, 0.0030 meter. That's the final answer. Oh, good. Okay, so this is how you need to deal with some charged particle. There are lots of contents, I know. We started from the basics of the electricities, charged particles, energies again, charged particle in the E field and the B field today. So, guys, this is something you definitely get in your school exams. I'm sorry, but I'm gonna bring some HSC questions related to this chapter next week. So we're gonna try some more problem solvings, and after that, if you have a time, we're gonna move on to the Morter effect, which is chapter 2. As I said, I'm planning to finish most of the module 6 before the school starts. So you actually finish like up to more than half of the module 6 by week 1. Okay. So try to challenge it, try to dip into it and study it. If you have any questions, please ask me. This is something not easy, I know that, but something that's very important. Okay, that's it.